Escomatic coil-fed automatic lathe model D2 and D4. Setup operator training system. Lesson number 10, the rotating tool head. Operation and adjustment of the rotating tool head is the same for both the Model D2 and Model D4 Escomatics. Located here below the feed rolls is the tool arm lever. The purpose of the tool arm lever is to transfer cutting information from tool cam number 1 and tool cam number 2 to the two tools mounted on the rotating tool head. Both cam followers are mounted on this cam follower end of the tool arm lever. The cam followers ride on only one cam surface at a time. Both cam followers are in contact with the cams only at the changeover point on the cams and camshaft 0. Located here is the split end of the tool arm lever. The lever is split to provide equal pressure on both sides of the tapered cone in the tool head. Located in front of each split end of the tool arm lever are the thrust pins. The purpose of the two thrust pins is to contact and move the tapered cone. One thrust pin is located behind the upper stock feed roll. The end of the split tool arm lever rides against the thrust pins but are not connected to them. This index line is located only on the thrust pin on the operator side of the machine. The purpose of the index line on the thrust pin is to indicate tool travel setting when the tool cam followers are set at their 0 reference. Located in the tool head is the tapered cone. Riding against the back of the tapered cone are the two thrust pins. The narrow end of the tapered cone faces the front of the machine. The tapered cone will travel back and forth in the tool head. Pressure from the thrust pins will force the cone to move forward in the tool head. Spring pressure will cause the cone to move back in the tool head when the pressure is released. Rises in the tool cams will cause the tool arm lever to push the tapered cone forward in the tool head. Falls in the tool cam will allow the tool arm to drop back, and the spring pressure will move the tapered cone back in the tool head. This is the counterbalance unit. There is one counterbalance unit for each tool position. Located at one end of the counterbalance is a roller. This roller rides on the surface of the tapered cone. Located at the other end of the unit is the counterweight. As the tool head rotates, the counterweight forces the roller end of the counterbalance against the tapered cone. This is the counterbalance unit lock nut. The lock nut holds the counterbalance onto the tool holder shaft. Any movement of the counterbalance is then transferred to the tool holder. At the 0 point of the main camshaft, Tool 1 and Tool 2 are set to a specified safe distance from the stock. The safe distance is usually specified on your layout sheet. The safe distance is usually set to 20 thousandths of an inch. The purpose of the safe distance is to assure the tools are clear from the stock when the machine is cycled to a stop. The safe distance also allows the tools to approach the stock before cutting starts. This is the view of the two tool holders and the counterbalance units as they ride on the tapered cone. Rotation of the tool head is counterclockwise. During operation, both roller ends of the counterbalances ride on the same diameter of the tapered cone. Notice that the tools sit on opposite sides of the stock guide bushing. Because the tools are mounted on opposite sides of the bushing, one tool will move into the stock as the other tool moves away from the stock. As tool cam number 1's radius increases, the tool arm lever will be forced up. This will cause the thrust pins to force the tapered cone forward in the tool head. As the tapered cone is pushed forward, the small roller end of the counterbalance will begin to ride on larger diameters of the tapered cone. This will cause number 1 tool to swing into the stock. Tool number 2, being mounted on the opposite side of the bushing, will move away from the stock. After tool number 1 passes through its safe distance, the tool will begin to cut into the stock. As the cams continue to rotate, tool cam number 1's radius will decrease. The tool arm lever will drop back. At some point, the cam follower will begin to ride on tool cam number 2. As tool cam number 2's radius decreases, the tool arm lever will continue to drop back. This will allow the spring pressure on the tapered cone to force the tapered cone and the thrust pins back. The smaller roller end of the counterbalance unit will begin to ride on the smaller diameters of the tapered cone. This will result in tool number 1 moving away from the stock. At the same time, tool number 2 will move toward the stock. After tool number 2 travels through its safe distance, the tool will begin to cut into the stock. Tool number 1's cutting force comes directly from the rises in its cam surface. This will cause tool number 1 to cut into the stock with a positive force. Tool number 2's cutting force comes only from the rotational forces on its counterbalance and the return spring of the tapered cone. Because of tool number 1's positive cutting force, it is usually used for heavy cutting, cutting off, and knurling. Tool number 2 is usually used for light cutting and sometimes cutting off. Located here above the tool cam followers are the 2 cam follower lock screws. The purpose of the cam follower lock screws is to lock the cam followers in the cam follower holders located in the follower end of the tool arm lever. These lock screws are loosened to remove and change cam followers. Located here on the cam follower end of the tool arm lever are the micrometer lock screws. There is 1 micrometer lock screw for each of the tool micrometers. Located on the top of the cam follower end of the tool arm lever are the micrometer adjustments for tool number 1 and tool number 2. The micrometer adjusting screw closest to the machine frame is used for depth of cut adjustments for tool number 1. Tool number 2's micrometer for depth adjustments is located here. Located at the base of each micrometer are these graduation marks and index line. Turning the micrometers clockwise will increase the depth of cut. Turning the micrometers counterclockwise will decrease the depth of cut. Each gradation will result in a half-thousandths change in the part diameter. Adjustments using the tool micrometers are referred to as radial adjustments. These adjustments affect the radius and diameter of the part. Types of cuts that affect the radius of the part are forming and turning. Forming refers to cutting straight into the stock with no stock movement. Turning refers to stock feeding occurring during tool cutting. This is the adjustable micrometer stop located to the right of the tool arm lever. The purpose of the micrometer stop is to perform cylindrical turning of a part independent of cam action. The micrometer stop is only used for tool number 2 and is adjusted for operation only at the lowest point of tool cam number 2. This is the micrometer stop lock screw. The lock screw must be loosened to adjust the micrometer stop. Located here are the adjustment gradation marks and index line. Each gradation represents a change of 1/2 a thousandth on the part diameter. Turning the micrometer stop clockwise will result in moving the stop peg up, which increases the diameter of the part. Turning the micrometer stop counterclockwise will lower the stop peg, decreasing the part diameter. As the cams rotate, this stop peg lever, attached to the tool arm lever, will come in contact with the stop peg at the lowest point of tool cam number 2. Any further decreases in tool cam number 2's radius will not affect the part dimensions since the stop peg now supports the tool arm lever. Each tool position on the rotating tool head is marked. Also, each tool holder is marked. When the special tool holder for the knurl tool is used on the tool head, there may not be a tool position marking on the tool holder. Located here on the tool head is the axial adjustment screw for tool position number 1. There is one axial adjustment screw for each tool position. Located below the axial adjustment screw is the axial adjustment lock screw. The lock screw must be loosened to make an axial adjustment. This is the axial adjustment screw for tool position number 2. Located below the axial adjustment screw is the axial adjustment lock screw. Located above each axial adjustment screw is an index line. The index line is used as a reference against the gradation marks on the axial adjustment screw. These are the gradation marks. Each mark represents a 0.5 change. When adjusting the axial adjustment of a tool, you are adjusting the position of the tool closer to or farther away from the guide bushing. This will affect the length of the finished shank on the part. On the Model D2 and D4S schematic, adjustment of the axial position of the tools will also affect the radial adjustment of the tools. This will happen because as you move the tool axially, you also move the position of the counterbalance riding on the taper cone. This will cause the radial adjustment to change. For a 1/1000th change in axial adjustment, the radial adjustment will also change by 1/1000. These are the tool holders. Each tool holder is labeled as to which tool it will hold. Each tool holder has 2 lock screws to hold the tool in position. On top of each tool holder is the tool centering adjustment screw. Whenever a tool is installed, the tool should be centered. Centering a tool assures that the tool's cutting edge will move through the center point of the stock. This will provide a clean cutoff of the finished part. These are typical cutting tools used on both the Model D2 and D4S schematics. The tools are triangular shaped and made of carbide. The tools are approximately 1 inch long. Each tool, depending on the part and design of the tool, may perform the function of turning, forming, chamfering, and cutoff. Some tools will be designed to perform 2 functions at the same time, cutoff and form. This is a tool drawing showing a typical tool angle and cutting edges. This tool is used for cutoff and chamfering to produce a finished part. This is one of the cutting edges of the tool. This edge is used to cut a radius to size on the finished part. This is the cutting edge that produces the chamfer on the part as the tool cuts off. This is the 12-degree rake angle of the tool. 12 degrees is the typical rake angle used on the tools. This shows the tool rake angle in reference to the stock. The tool will rotate counterclockwise around the stock. As the tool cuts, chips will form on this surface. This surface is called the face of the tool. This is the face of the tool. When the tool becomes dull, the tool is sharpened. This is the only surface to be ground for tool sharpening. These are some of the clearance angles used on the cutting tools. The angles are usually small. The purpose of the clearance angles is to assure that only the tool cutting edge is in contact with the stock as the tool cuts. If more of the tool contacts the stock, the tool will overheat. This is the width of the tool. The width of the tool is important in controlling the length of the part and shanks produced on the part. This dimension is the tool width. This dimension should be checked against the tool you will use for the job being set up. The tool width should be within the tolerances given on the print or layout sheet. This completes your television training tape on rotating tool head. You may watch this tape as many times as necessary to fully understand the material. When you have finished, return to the operator booklet for your next step.